Hello everyone, welcome back. So, we have looked at row scheme, Ruzano scheme, HLL, HLLC schemes, and we solved the problem of the shock tube. And what we realized that while these schemes, especially the row scheme and HLLC, provide a decent prediction of let us say contact discontinuity, shock, and the expansion fans, the accuracy can be improved further, because if you look at the results compared to what we see from the exact solution, there are still some dissipations that you note close to the discontinuity. For example, if you look at here, so this is where we stopped in the last class. Okay, so here you have, if you look at the blue curve here, I mean they are highly dissipated here and here. So, the question is, can we improve these predictions, right? So, the one way is to that you make the grid size finer and finer, and then there is accuracy will improve. But can we make the schemes high order or high resolution, so that you can get better accuracy on the same grid? So, that is the question, because if you increase the grid size, naturally the cost will increase proportionately. Okay, and if you can have the higher order scheme, there will be some additional cost because of the higher order calculations, some more calculations that you have to do compared to the first order, but then the cost will not be as much if you have to increase the grid size to get the same order of accuracy, right. So, that is the principle behind trying to go for high order accuracy. And when we are talking about the computational gas dynamics and flow which has got the shocks and expansions, it's a slightly different business, because you have strong discontinuities at different locations that you need to deal with. If the solutions are smooth, for example, let us say you are talking about incompressible flows or flows which does not have basically such big jumps, then I mean you may not require these kind of shock capturing schemes or basically special treatment near the discontinuities, right. But because you are dealing with these complicated flows, we need to have special treatment, and we also need to increase the order, and we need to be very careful, because if you increase the order, as we have seen earlier in the case of lax band drop, you will start seeing wiggles, right. So, we go back to the schemes that we studied earlier. If you recall the lax band drop scheme that we have seen earlier. So, this was the central differencing part, and then plus we had some diffusion part, and this was second order. Okay. So, we will basically focus our discussion based on this scheme, because if this is second order, can we use this kind of schemes without basically the additional wiggles, or what we discussed earlier is that the valuation of TBD, right. So, the total variation is was increasing for this particular case. So, can we basically keep the total variation under control. Similarly, we had this beam warming scheme also. So, this is basically one sided scheme. So, you have I minus 1, I minus 2. Okay. So, pure upwind 3 stencil I minus 1, I minus 2, and this was also second order. Okay. So, as I mentioned that, I mean both are similar schemes if you look at it. So, this is basically they are both derived from the Taylor series expansion. That means, if you look at the Taylor series and let us say you write in terms of n plus 1, the u n plus 1 will be u n plus delta t du by dt plus delta t square by 2 du by dt square, right. And if you use this conservation equation, du by dt equal to minus c du by dx. Okay. So, then this is u t equal to minus c u x, and if you take second derivative, we have discussed this earlier, this will become c u square u x x. So, replace this and this by the corresponding x and x x, basically first and second derivative, you will have these expressions. Now, for this is what you have in this both these forms. Okay. So, this is n plus 1 is n, and this is actually naturally at n. Okay, these are all at n. So, now the first derivative, the u x, we have used central differencing here, we have used one sided scheme. Okay. And then we using 3 stencil. For u x x also we have used the central differencing here, and you have used the one sided stencil here. Okay. So, these are basically lax band drop beam warming. Now, the way I have been discussing these schemes in the context of finite volume is that we are basically trying to solve the Riemann problem, okay, and then we are calculating this I plus half and I minus half, okay, and then you take this flux differentiation scheme, okay, del t by del x, and then you have basically u I n is equal to. So, this is how you have been solving. So, you have been casting the equations, I mean schemes like the row scheme or HLL, HLC, all in this form. Okay, even the upwind we can cast in this form. So, can we cast these equations for example in this form? So, let us focus on Lex van der Rohe. Okay, we will also discuss little bit about beam warming, but both are same principle, both are second order. Okay, and in both of them you have Wiegels. Okay, if you start using even for linear convection equation, provided you have some discontinuities. Okay. So, let us look at the Lex van der Rohe scheme in the context of finite volume, right. So, as we have discussed earlier, now let us say we have a volume like this, okay. This is I and this is I plus 1, okay. This will be I plus half, this is I minus half, okay. This is the cell center, okay, and we have been calling this U average, right, whatever the value, average value at the cell center. So, you can write that in the finite volume form. So, what I have done here, I have just replaced this U s with U average, okay, in this cell finite volume, and then we can write in the flux difference form, okay, what is whatever the fluxes which are getting exchanged from this and this side for a given cell I, and the difference between those fluxes is what gets updated in every time step. So, this is the previous time step and something got in, something got out. Remember, this is negative sign here, and in the fraction of time, which is basically delta t, I mean delta t by delta x, you can call it, and this is what is the this is how you get the update, right. So, in this Lex van der Rohe scheme, you can write this flux formulation as half f u I plus f u I plus 1. This is the averaging part, and this is the difference part, okay, delta t by 2 delta x c f u I plus 1 and f u I, right. So, can you prove it? Yes, you can just put this equation. So, f is equal to now c u, right. So, if you want to do this, this will become f I plus half. So, this is c. So, this will be c by 2 u I plus u I plus 1. Okay, I am not putting the bar on top, but you can understand this is for the cell average quantity, and minus delta t by 2 delta x, okay, and this is c. There is already one c and there will one be c from here. This is c square u I plus 1 minus u I, and then similarly if you can write I f I minus half, that will become c by 2, this will become u I minus 1 plus u I minus delta t by 2 delta x c square u I minus u I minus 1. Okay, this is 1 minus 2. So, if you do 1 minus 2, okay, so you will have the flux difference f I plus half minus f I minus half, that will become, so c by 2, and this will get cancelled out. So, this will be u I plus 1 minus u I minus 1. So, we are recovering the term which is like this. Remember, we also have this delta t by delta x, right, and if you look at these two terms. So, this is basically the central differencing part, and then if you look at these two terms. So, this will become c square. Okay, so, I do not think you will have this, yeah, you will have this. So, c square delta t by 2 delta x, I am just writing this part. So, this will become u I plus 1 minus 2 u I and plus u I minus 1, okay, and this will become plus sign. Okay, this is minus and this is plus. Okay, so, this is what you have from here. So, this second part is gotten from here, from this part, and the first part is from this, right. So, we have now casted our expression. So, this is the proof, okay, this is I plus half and this is I minus half, and if you do the difference between the two, you have the central differential part and the diffusion leg part, right, and which give we recover our Lex van der Rohe equation. So, why did we do that? so what we are trying to do, we are trying to see that if you can do something in this equation in the flux form, so that whatever wiggles that you have. So, let us say this is your square wave that we have been looking, and if you look at the solution, you may have wiggles here, or you may have wiggles here or here or here. Okay, so, can we get rid of these wiggles, which basically increases our total variation? That is our purpose, and that is why we are casting in different form. So, we have casted in this flux difference form. We will also look at how we can recover the same expression, the Lax-Van-Troff expression, by considering a linear variation inside the cell instead of a constant variation, okay, or the constant assumption. Okay, so, this is your I plus half. You can cast it again in a different form. So, this is your CUI, and plus you have these two terms. So, you can write it as CUI bar plus maybe you can have this UI plus 1 minus UI, okay, and then you can have C by 2 and 1 minus C delta T by delta x, right. So, why we have written in this form? Because if you write in this form, so then you have f I plus half minus f I minus half will become C U I minus U I minus 1. Remember, I am talking about C greater than 0 as of now. For the most of the discussion, you have lab C greater than 0. If you have C less than 0, you know that the expression will be even the upwind formula will be U I plus 1 minus U I, right. But C is greater than 0, then upwinding is basically I and I minus 1, right. So, for most of the discussion in today's class, I will be focusing on C greater than 0, but you can, if you have C less than 0, you can have this the counterpart that you can derive, right. So, then you have this first upwinding part, and then we will have these two part which will be coming up because of the correction in the upwinding. So, this is basically the first order, okay, and then you have some correction which is coming because of this term, right, and we have to basically work on this part so that you get the higher order, still we do not have wiggles. Okay. So, till now what we have done, we have basically considered a constant value in all the cells, right. So, whatever value that we have, the UI bar, that was constant, and that is why we are getting the first order formulation. But between the boundary to boundary, let us say this is my I minus half and I plus half, you may have a linear variation like this. Okay, this is your cell center, okay, and this is the variation that we have, okay, or you may have here like this or here. So, if you assume a linear variation, then it may increase you, it may give you the higher order. Why? Because see, if you consider it, this is the boundary and this is the boundary. So, this is boundary to boundary, and we have earlier considered I mean basically piecewise constant, and now we are going from piecewise constant to piecewise linear. So, we are also considering the variation of the cell average within the cell. So, you have some value here and some value here. So, basically what we are doing, we are correcting our assumption that we had earlier, that the values should remain constant within the cell, to another approximation which is a better approximation, that it varies linearly. If you go to, let us say, the finite element kind of formulation, you can also go to maybe the quadratic variation, you will have this HP formulations, you can have a polynomial variation within the cell or within the element in that particular case. So, right now we will focus on the linear variation. So, what we are saying is that instead of a piecewise constant data, we have this piecewise linear data in every cell, right, and we will see that by considering the piecewise linear, we are actually recovering the second order. So, then you will not have only this part, but we also have this part. Okay, what is this sigma I n? Sigma I n is basically delta u by delta x. Okay, this is basically the slope, okay, and this slope delta u, basically it can be u I minus 1 and x I minus 1, or it can be u I plus 1 minus u I by x I plus 1 minus x I, okay, or you may have the central differencing kind of scheme, okay, x I plus 1 minus x I minus 1. Okay, so, we do not know, we have just assumed that there is a linear variation, and because of the linear variation, and let us say you have something which is varying linearly, and you know the slope which is I mean sigma I here, right. So, you want to find at any point x I. So, you will have u y whatever the value that you have, the constant value, the cell average value plus sigma I n and x minus x I, right, and this will be for every I minus half to I plus half, we will have a different linear variation, right. So, the idea will be to assume the linear variation and then we can solve the Riemann problem from whatever value that you get from the interface, you will get something from the left, something from the right, okay, and solve the Riemann problem at every interface. Okay, what happens when you have the linear reconstruction? So, for a linear convection equation, let us say ut equal to c u x, we know that whatever, so you have x t will be u 0 x minus c t, right. This is what we had discussed earlier, where c is the characteristic speed, right. So, similar thing you can write from here also, that T n plus 1 is equal to x c minus c delta t. So, delta t is equal to T n plus 1 minus T n, right. So, if you assume that, and now we have a linear reconstruction, right. So, u I plus half. So, this is my I, this is I plus half, this is I minus half. So, this is my cell volume, right. So, if you want to find out what is the value at I plus half, because there is a variation which is with sigma I. So, we will have this distance is my delta x by 2, this entire thing is delta x, right. So, this will become u I plus delta x by 2 into sigma I, okay, where sigma I is, as we discussed, this is delta u by delta I, delta u I by delta x I, right. So, when you will use this formulation, so the convection at a given time tau, very small time tau, okay, that will be u I plus half, this is the initial value minus c tau sigma I. Why this c tau sigma I? Because this u 0 is equal to x minus c t, right. So, this is my initial value, and then you have basically c and tau, and now since there is a variation in u, so you will have basically something called delta u by delta x. So, you have c tau is the time which has it has passed, okay, because tau is the time step that we are taking, and c tau by delta x is something which is basically the fraction of time which has passed, fraction of cell volume that has moved. Let us say this is my delta x. So, this is my c tau, and then whatever the variation that we have, okay, which is basically the delta u. Right. So, this is, I hope it is clear that when you have the linear variation, you can write at very small time tau from the initial value I plus half and minus c tau sigma I, right. So, now you want to find the flux, so you have to get this I plus half and I minus half, okay. So, then you average this over the time step which is over delta t. So, this is going from 0 to delta t. So, this will become u I plus half, this is the same thing, and this will become c delta 2 by 2 into sigma I, right. So, this is the value of u I plus half after time delta t, okay, when it has undergone through this linear convection. So, now when you want to write your flux, okay, so the flux will be c u I plus half plus minus c delta t by 2 sigma I, and what is u I plus half? U I plus half is u I plus delta x by 2 sigma I, and then you have minus basically c delta t sigma I. So, finally, you can write this flux f I plus half as c u I plus c by 2 sigma I delta x by c delta t, delta x minus c delta t. Remember, I have not specified what is sigma I yet. I am only saying that it is some difference in the velocity or whatever variable that you have, and divided by the distance delta x, that gives us the slope, because you have a linear variation, right. Now, let us take one form of sigma I, which is the downwind slope, okay. Upwind is u I minus 1 by delta x, okay. This is the downwind, because now we are considering, remember, c is greater than 0 always. So, this is u I plus 1 minus u I. Now, you put this value here in sigma I. So, I put it here, and now you basically recollect the term. So, rewrite in the forms u I plus 1 minus u I, and this is nothing but the value that we had seen earlier. Okay, this is the same thing that we have seen earlier. Yeah, this is the form that I discussed earlier, or this one, right. So, what we did by considering the downwind slope across every cell, we are getting the Lax van 't Hoff equation, right. Now, what if we consider the upwind slope? So, if you have this upwind slope, then sigma I is ui minus 1 by delta x. Okay. And if you put this upwind slope here in sigma I, okay, and rearrange like I have done here. Okay. So, ultimately what we will get is nothing but the beam warming scheme. Okay. So, remember we started with the flux difference formulation and we said that there is a linear variation of the variable of the quantity across every cell, and by considering linear variation, that means how do you get the slope? Either you can take the slope. So, if you have let us say 3 cells like this, okay, and you want to get the slope here. So, either you can get the slope from here or you can get the slope from here. Okay. So, if you are getting the slope from here, this is your upwind, then you get the beam warming. If you are getting the slope from here, then you are getting this is the downwind, and then you are getting the lax band trough, right. You can also take an average of the two, basically centered slope between the, I mean take the average of lax band trough and the upwind, which is nothing but kind of the central differencing, okay, ui plus 1 minus ui y minus 1 by 2 delta x. So, we are basically considering both the left and right to get the slope, and this gives you something called From's scheme. We have not discussed this earlier, but yeah, this is you are seeing that how by just going through this flux difference formulation and by considering a linear reconstruction, we are getting these different schemes. So, now you put this value in the place of sigma I in the earlier expression that we saw in the last slide, and you will get an expression like this. Okay. Now, you see that here we are using the upwind slope. So, I will show you the plot where you will have V gulls which is appearing ahead of the shock. In the case of lax band trough, it is behind the shock, okay. And in the case of From's scheme, it will be basically because we are taking the average of both the two. So, something will be ahead, something will be behind, they will cancel out, but still if you run it for a long time, you will see that there will be oscillations which will develop, okay, and they will eventually wiggle. So, all these schemes that we discussed, whether it is lax band trough or beam warming or From's scheme, okay, they are all not TBD because they develop wiggles and that leads to increase in the total variation, right. So, this is the example that I was talking about. So, if you look at the red curve which is the lax band trough curve, okay, which is downwind, okay. So, you can see that you will have this lagging phase error. So, before the discontinuity you have this wiggles which get developed, okay. We are using the downwind slope here. If you use the upwind slope which is the beam warming, so you have wiggles ahead of this, okay, in the beam warming. So, you can also do the von Neumann analysis that we discussed earlier, and you can get the same behavior that the lagging error and leading phase error, okay. So, this is the beam warming, and you can also look at the From scheme which is basically the between the downwind and the upwind, and you see that if you can note here the wiggles are small, but they are still being developed here, okay, both the sides, okay, both the downwind as both the ahead of the discontinuity as well as the behind the discontinuity. And if you look at, so this is the square wave, this is the propagation of this square wave. We are also propagating a simple Gaussian wave, and you can see that Gaussian wave they are almost, I mean all these three schemes they preserve the magnitude a lot. If you use upwind scheme, it will become something like this, okay, it will become like this, okay, the magnitude will go down, but because these are second order, they will behave very well if the solution is smooth, right. But as soon as you have some discontinuities like this, okay, you will start seeing this behavior where you have a lot of wiggles, okay. So, these are some of the properties that we have discussed here already. The similar concept why we get these wiggles is related to something called overshoot and undershoot, okay. So, let us say if you are trying to construct, so we have basically these points, and instead of having, so if you have a piecewise constant, then what will have, you will have basically a line like this, okay, and a line like this, and you will solve the one problem here, correct. Now, say that you want to go for the first order correction, right. So, if you go the first order correction and let us say you take this I plus 1. So, let us say this is my I plus 1 and I, okay. So, you want to take a slope which is going by this, you calculated the slope and applied it between this is I plus half and I minus half, okay. So, this is my cell, okay, this is my cell, and I applied the slope which got calculated from I plus 1 and I, So, this is basically the Lax-Van Troff. Okay. But once it propagates, so this propagates on the right hand side. So, let us say it got propagated by C delta t here. Okay. And now, if you take the average of this. Okay. So, when you take an average of this, you will have let us say the cell center somewhere here, okay, or here. So, what has happened is that there was no overshoot in the problem initially, but because of this linear construction that we got, we basically did by considering the slope from I plus 1 and I, we got created an artificial overshoot. Okay. It has basically gone above the value that is expected, and this is what will develop the wiggles. Okay. If you let us say consider I and I minus 1, for example, in the beam warming scheme, okay, then what we will have? We will have basically this one going down here, and you will get develop something called undershoot. Okay. So, the TVD says the total variation diminishing property says that we should not have overshoot and undershoot in our solution. Okay. It should be, if you recall, we have talked about this monotonicity preserving schemes, and TVD schemes are monotonicity preserving schemes. So, if you are developing artificial overshoot and undershoot which are not there in our earlier solution. So, we are basically disrupting the monotonic behavior of the problem, and that will not be TVD, and that will eventually develop wiggle. Okay. So, we need to avoid this. Okay. And yeah, this is what is the TVD scheme. If you look at the first order upwind scheme, this is naturally TVD, because it removes variation so aggressively that it is dissipative, right. So, naturally the TVD will go down or it will remain constant. Okay. Once again recall that TVD was given as ui plus 1 minus ui. So, every time if you have a wave like this, okay, the initial wave. So, the TVD will be, so this is all 0, okay, this is all 0, and let us say this is 0 and this is 1. Okay. So, the total change here I plus 1 minus I will be 1, total change here I plus 1 I is 1, this again here is 0. So, if you add all of this, the TVD of this system, initial TVD, okay, will be equal to 2, and if you develop wiggles, then you will have these things coming up, okay, and because of that your TVD will increase, okay, which is not a good property, because it will eventually develop wiggles and it will corrupt the solution, will have dispersion error and so on and so forth, right. For the TVD scheme, so the total variation at n plus 1 should be less than or equal to n, which is naturally satisfied by the all the first order schemes, because they are dissipative. Okay. But in the second order scheme, for example, Lax-Van Troff, it is not TVD, it creates new extrema, overshoots or undershoots, okay, near shocks or any discontinuity, and which leads to the increase in TVD, total variation. So, what we need to do? We need to basically devise a formula or a technology which can basically take care of all these new extremas. So, it should not allow to develop new extremas. So, when the solution is smooth, right. So, for example, what we saw like this, right. So, you have a smooth variation. In this case, it should be the second order, right, but whenever you have this discontinuity like this, okay, then you have to basically switch the this Lax-Van Troff to something like first order or the upwind, so that you can, it can capture these things perfectly. Okay, and in this region also you can have basically the second order solution. Also, if let us say if your shock resolved in let us say 5 points or 10 points, okay, if you use this Lax-Van Troff scheme. So, once you have basically avoided discontinuity and you want to resolve the shock, again within the shock you can have this scheme to be the second order. So, that is what is called limiter. So, what will it will do, that it will limit the slope in the regions where you have discontinuities. Okay, in other regions it will allow it to be the linear construction like Lax-Van Troff, but wherever it sees the discontinuity, it will switch it off and it will go to the upwind scheme. If you look at the limiters in the next class, and we will discuss how it can be used successfully for the problems that we are discussing. Thank you very much.